It is now. I'll back up again. All right, so regulation of pyruvate dehydrogenase was step 0. High concentration of NADH or high concentration of acetyl-CoA compared to the free versions causes E2 to be unable to grab another acyl group. So the reaction doesn't continue forward. We just end up with TPP stuck with hydroxyethyl TPP, and we don't move forward.
Because there's so much acetyl-CoA already made, the E2 is not going to give off its acetyl-CoA, so it's not going to get involved.
Yeah, because right, the body has so much acetyl-CoA it doesn't need anymore, so it turns off the making of it at that step.
Which keeps E2 from taking.
Yeah. It's kind of like a feedback inhibitor. It's telling the enzyme, I don't need any more of this, so just wait until the concentration decreases, then it'll start making it again. The other way we can regulate step 0 is using covalent modification of E1. Let me zoom in a little bit. All right, so E1's our molecule enzyme that has the TPP attached to it. So E1 can be inactivated by phosphorylation of the active sites. So we end up phosphorylating E1 when we have high concentrations of NADH and acetyl-CoA, like we did up here in the other option. But those high concentrations turn on the enzyme pyruvate dehydrogenase kinase. And what do kinases do? Phosphorylate. They throw phosphoryl groups on things. And so this kinase phosphorylates pyruvate dehydrogenase. And by phosphorylating it, it's no longer able to take in a pyruvate molecule. It turns off E1. So there's two ways that the enzyme complex is turned off. One, NADH and acetyl-CoA concentrations prevent E2 from taking on any more acetyl groups. And the pyruvate dehydrogenase complex E1 is phosphorylated. And so it can't take on any more pyruvates. And there's a really long signaling mechanism that turns on all these other things. It turns out when you have high glucose concentrations, right, it turns on your insulin production. Insulin production helps turn on high concentrations of NADH and acetyl-CoA. And insulin concentrations that are high turn on these, and these turn on kinase. So really, it feeds back all the way back to the original very top of your glucose system. So lots of sugar actually turns off this too. Questions on our two ways to turn off step 0? regulate, not necessarily turn off. You can turn it back on. Okay. In that case, there are our rate controlling enzymes. So just like we have 3 possible rate controlling enzymes in glycolysis, but really PFK is the RDS of glycolysis. If you don't know that, star that, because there's definitely a question about that in the test. RDS, PFK, good. So in the citric acid cycle, there are really 3 possible rate determining steps for this cycle. We see that citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase multi-enzyme complex are the 3 that have delta Gs that are negative. The rest of them operate at around 0. Flux metabolites through the citric acid cycle is proportional to the rate of oxygen consumption. Guess I'll write it up here. Because oxygen consumption, NADH reoxidation, and ATP production are all tightly coupled, which means they all depend on each other. All right, depending on how much oxygen is being used by your body, you'll either head down the pyruvate to acetyl-CoA path, or maybe you'll head down the lactic acid path. And then that tells your body how much ATP to make. Those are all interrelated with each other. Since they're interrelated, the citric acid cycle The citric acid cycle is going to be regulated by feedback mechanisms that are related to the production of ATP, NADH, and eventually oxygen production. Through 3 main mechanisms. So the feedback mechanisms are going to be related to either substrate availability, product inhibition, or a competitive feedback. A few people still writing, I'll wait. Okay. So just like I had in the previous slide, the regulators are going to be acetyl-CoA, NADH, and then the intermediate that is going to help regulate is the oxaloacetate molecule. Well, why would it be that molecule of all the options we have? Right, because of where it's located. It's the molecule that has to interact with acetyl-CoA to head on to the next step. So it is the regulator of the cycle, because if there's a lot of it, then we can keep going. If it's reduced, then we'll keep pulling forward. So it's kind of the keystone in your citric acid cycle. Let's see, flux varies with substrate concentration, right? And flux is a way of describing flux is another way of saying rate of production, right? If you have a high flux, you have a high production path. If you have low flux, not a lot of things are passing through. All right, so looking at, it's a cooler looking picture in color. So, these little octagons are supposed to be stop signs. And these little circles are supposed to be go green lights.
Is this picture in our book?
It is in your book. All right, so if we're looking at these different feedback pathways, you can see that there are a few molecules, one, obviously NADH, and a few other intermediates that are able to turn on and off the entire cycle depending on what they're doing. So NADH has the ability to regulate several reactions in the citric acid cycle. Right, every reaction that's a redox reaction, which in the citric acid cycle is the majority of the reactions. So anytime NADH is produced or used, they have the ability to regulate that reaction. Let's see what else. So looking at citrate, if there's a lot of citrate, it'll turn off this step, which is the isocitrate dehydrogenase, which is the official name, right, was NAD plus isocitrate dehydrogenase. So obviously the concentration of NAD plus the concentration of citrate will affect that reaction. What else do I have? Your calcium concentration will also affect right through the cycle. All right, there's a few different places where we use calcium, acts the same as magnesium, and holds on to negative charges. We saw up here we used calcium so that we could eliminate a carbon dioxide molecule from the proper end of the isocitrate. It cleaved off the one off the side, not the one off the bottom. And so we need calcium both times we eliminate a carbon dioxide molecule to keep the charges from being eliminated. Either, same thing. So anything with the 2+ charge. So they're kind of interchangeable. Magnesium, manganese, calcium, they all work in the same way. And succinyl-CoA is a competitive inhibitor with acetyl-CoA in the citrate synthase reaction. I'll just hold the arm. So, right, succinyl-CoA, if you follow the dotted line, comes all the way up here and can turn off step 1 of the reaction. That's because succinyl-CoA, right, that's the membrane-bound, and well, succinate-CoA synthase is the enzyme-bound one, which feeds into the electron transport chain by making a GTP, which is really the same as an ATP, and sending 2 electrons, which are symbolized as Q in your citric acid cycle, down through the electron transport chain. So this molecule is getting information back from the electron transport chain about how much ATP is needed / already have, and can come back and turn off the entire cycle. So, kind of a big deal, enzyme molecule. All right, last thing. Pathways that use the CAC intermediates, citric acid cycle intermediates. So we mostly talk about, right, glucose to pyruvate to acetyl-CoA with the idea that we're making GTP, really, and sending some electrons down through the electron transport chain. However, citric acid cycle is considered the metabolic hub of your entire body because it makes intermediates that are used by 3 main other biosynthetic pathways. All right, so here's our pyruvate that came from glycolysis to make acetyl-CoA. Here's our regular citric acid cycle. Well, citrate is needed for cholesterol and fatty acid production. Alpha-ketoglutarate is needed to make any amino acid your body has. Succinyl-CoA makes porphyrins, and it's also how isoleucine, methionine, and valine are specifically made, as well as all odd-chain fatty acids need succinyl-CoA to get started. Fumarate is the amino acid intermediate, aspartate, phenylalanine, tyrosine. Malates need to make glucose production in your body, and oxaloacetate, it also feeds into the amino acid biosynthetic pathway. So let me just write down 1 or 2 things about each of these. If for some reason you've not eaten enough glucose that day, your body has the ability to make its own. Never an issue in my diet. But if for some reason you're not intaking enough sugary items, your body can use oxaloacetate, convert it to malate, right, oxaloacetate back to malate, or it could use malate depending on where the buildup is. It's usually oxaloacetate's the buildup, because that's the one that needs the glucose coming from, well, needs the pyruvate coming from this cycle down here. So oxaloacetate is typically the one that's building up. And if you take Biochem 2, you'll spend quite a bit of time talking through how you make glucose. So all of these, glucose biosynthesis, fatty acid synthesis, amino acid synthesis, is spent Biochem 2. Yeah? There are other ways for us to make pyruvate. So your body has a few other pyruvate mechanisms if glucose isn't present. But yeah, the easiest way to make pyruvate is through glycolysis. There's some other back routes around that. Mm-mm. We've talked a lot about fatty acid and amino acids, so I'm just going to say that so both fatty acid synthesis and amino acid synthesis require citric acid cycle intermediates. There's a bunch more stuff I could tell you about how they get converted, so they can transport, right? Because where does all citric acid cycle occur? It's in the mitochondria, but all of these biosynthetic processes occur in the cytosol. So part of the issue is converting them to a compound that can transport across the membrane, so it can do the other synthetic processes. But that is for Biochem 2. Leave you on a cliffhanger till next semester. For the 3 people I think are going to take Biochem 2. You'll just have to tell everybody else. Maybe 4 people. So. And I think Davin. Yeah. Maybe Meredith? Yeah? Excellent question. How many people are taking Biochem 2? 5. 6. Yeah, where's Megan at today? Cookie. She turns 21. She thinks she can skip class. If you're listening later. All right, that is the end of stuff. Lots of stuff. All that stuff. Yes.
2 questions.
Ask away.
Number 1, you said it was hard for us to know abbreviations, correct?
Yes.
Is it okay if the abbreviations are ones that can be similar in a different class and find this?
Sure.
Okay, cool.
Sure.
Second question. Was I mishearing earlier when you maybe sort of mentioned that you might consider meeting this Monday?
No, I'm not moving it to Monday.
Not even option for a vote? Is it for discussion?
I mean, I really don't see any advantage of moving it to Monday because half the class has already planned on taking it on Friday. Yeah. Yeah, I think we're just going to do it on Friday. Because the majority of people have already spent their time studying for Friday. Plus, I know there's a large proportion of us, not me, who may not be here on Monday because it's Thanksgiving week and have already made plans to be out of town. So, or maybe that's just my Gen Chem class. They all told me they're going to be gone all week. So, how about I answer any questions about step 0 or anything else? Any questions besides? Olivia, what do you got?
Go over the roles of the,
Oh, the quiz?
yes.
Yes. Okay, in that case, let's look at that. Let me find my other slides. All right, so on your quiz, the question was, what are the roles of the different intermediates? I don't have a copy of the quiz with me. Let me read it real quick. The cofactors. Okay. What are the roles of the cofactors, and how do they play a role? All right, so there's 5 cofactors. Right, there's TPP, lipoamide, CoA, FAD, NAD+. Definitely know those 5 cofactors. All right, TPP, lipoamide, CoA, FAD, NAD+. Yes, we're going over the one on the quiz.
Is lipo after the famous?
I think, hold on. That was a brief. Yeah. Yeah, lipoic acid and lipoamide are going to be used interchangeably, both in your textbook and just in general. Sometimes, some textbooks refer to TPP as biotin, which is kind of a funky thing. Right, TPP comes from vitamin B2. So there's some questions in your book about vitamin B2 converting to a bioamide, because TPP stands for I have it written down someplace. Thiamide, pyruvate, thiamine pyrophosphate. And so vitamin B2 is a thiamine. And if you don't have enough vitamin B2 in your diet, you don't have enough TPP, and so your citric acid cycle can also slow down. So that's just a fun fact. Eat your B vitamins. Okay, neither here nor there. All right. So we're going to send in a pyruvate that we made at the end of this glycolysis. All right, so we made pyruvate at the end of glycolysis, and the point of step 0 is to turn that pyruvate into an acetyl-CoA. We're going to take 3 steps to do that. At the end of step 3, we've made acetyl-CoA. Steps 4 and 5 are to get our enzymes all back into the original shape. All right, so pyruvate is going to interact with enzyme 1, which is the pyruvate dehydrogenase, which contains a TPP. So the first coenzyme we're going to use is TPP. So now pyruvate has kicked off a carbon dioxide and is covalently bound to TPPE1. There now. Release that, made this. This is step 1. So now enzyme 1 needs to regenerate its TPP, right? Because it's an enzyme, it has to get back to its original form. And it's going to do that. It's going to regenerate this way. I'm writing way too big. So this is step 2. So now E1 and E2 are going to interact. The lipoamide, which was this guy, right, had this dithiol cycle in it. It's going to interact with the hydroxyethyl TPPE1 to regenerate E1 and to make the acetyl dihydrolipoamide. Right, so we had this dicyclodiol, and now I have transferred the hydroxyethyl off of this guy onto this guy. So I've just moved it and remade my TPP1. So that's ready for another pyruvate.
That's what you do right there is what?
This is still part, right. So it transferred this group from the TPP to the lipoamide. It just moved it from one spot to another. So now I have an E2 with a crazy thing stuck to it. So I need to get my E2 back. And I want to get rid of my acetyl group to make acetyl-CoA. So I have an acetyl stuck to a dihydrolipoamide. So what am I going to need to do that if I want to make acetyl-CoA? I need a CoA, right? So here we've used, this is our first cofactor. Here's our second cofactor. I'm now going to use some CoA. And this is step 3. So CoA comes into the E2 area, grabs the acetyl group, floats away with it. I've now made acetyl-CoA. So steps 1, 2, 3, make acetyl-CoA. But now I need to spend the last 2 steps getting my enzymes back into their original shape so they can go through it again. Right, so if I looked at what I had left here, right, that's what I have now. I've kicked off the acetyl group and now I have this lipoamide that's not a cycle. So I'm going to use enzyme 3 which was that guy. So enzyme 1 was over here. Enzyme 2 is here, and enzyme 3 is over here. So enzyme 2 and 3 interact. And I have an FAD. So what sort of reaction happens when you have an FAD? We have a redox reaction. So I'm going to oxidize this guy and reduce this guy. If I reduce this guy, I'm back to where I started. But now I'm going to have no, that's right. Right. FADH2. So they don't show this in the little picture in the book. It really goes through 2 steps. The FAD goes to FADH2 and that's reduced, and then goes through like another intermediate. But then here's our last 2 cofactors, right? We got our FAD and our NAD+, and everybody's back to where we started. So in order, you're going to use TPP in step 1, lipoamide in step 2, CoA in step 3, FAD in step 4, NAD+ in step 5. You do not have to draw that, but it may be easier to draw it than write it out in words. See what I'm saying? Like if I ask you a question about it, it may be easier to sketch it than to describe in words all the chemistry that's just happening there. Yeah, the level of detail. So if I asked you to describe this in words, it would be ridiculous. You'd have no idea what you're writing. But if you just drew me a picture, then you're fine. In general, I always accept pictures over a terrible description. So go with the pictures. All right, I have office hours this afternoon till 4, from like 1 to 4. I have office hours all morning tomorrow, part of the afternoon tomorrow. If you get confused or got questions.